Hi everyone. So we'll get started. Um, and then the rest of the class may be joining us later. But let's get started. Let me share with you my PowerPoint slides here. So today we are going to talk about chapter 17. It's the new chapter, okay? But we will not cover exam 3 here for chapter 17. So chapter 17 is not in exam 3, okay? I think it's just 15 and 16 will be covered in exam 3. All right. Let me also talk to you a little bit about exam. So we'll be doing pretty much the same thing on exam as we did last time, okay? But this time you are going to um, go to the Moodle site, okay? So this is what you will be seeing if you just enter the Moodle page of this class. This is what you have. So you only have a few documents listed here, and then the assignment, the rest of the assignment will show up. So you want to click Show More here. Okay. I have set up exam 3. So exam 3 will be next Wednesday, the Wednesday after we come back from the break. Okay. So exam 3 will be on Wednesday after the break. Okay. So again, I'll be sending you sending out the exam in email. So each of you would get different version of it, and then you'll be submitting your work here. Okay, under exam 3. Let me see. I think I set it up so you can have until 2:30. Okay, so I'll be sending out exam about 12:30, and then you'll be submitting it by 2:30. Okay, so this is where you'll be submitting your exam 3 this time. All right. It's a similar format, like it's going to be open book. Okay, so but you still need to study the material, right? Because if you didn't study, then you wouldn't know where to start each of the problems when it gets to the time of the exam. Okay. All right. Do you have any questions on exam 3? You can speak up, or you can text in the chat. Either way. Also, homework night is still on Wednesday. Okay, so that's another reminder item. So if not, let's get to the lecture part of the day. We'll be looking at chapter 17 here. So today we'll be just talking about the first section of the chapter on moment of inertia. Okay, so we'll take a few examples and then also a few quizzes so that we can be familiar with how to determine moment of inertia of a rigid body. Okay. So again, the usual stuff we'll be doing reading quiz, lecture, and then quizzes, small quizzes, and then at the end, if we still have time, we can look at the group problem solving. Okay. Let's start with the quiz here, the reading quiz. All right. So go ahead and then send me your answers in the chat privately. Okay. Right, I think everyone on board has submitted your answers here, so we'll take a look. On the first one, mass moment of inertia is a measure of the resistance of the body to. Okay, so this one should be C, the angular oscillation. Okay, so let's see here. On the second one here, it says mass moment of inertia is always. It's defined as like integration of r squared times dm. So that should be always a positive number because you're doing r squared. Okay, and then dm should be positive as always. So then it's positive quantity. Okay, so it's going to be C and B on this one, on these two. Okay, C on the first one, B on the second one. Okay. All right, so we'll take a look on the lecture of the day. So mass moment of inertia, okay, this is, so if you have a body, rigid body that is rotating with an axis, okay, going through its body, or many times it could be like outside of the body, okay, so it's with respect to a certain axis, okay, so let's take an example of z-axis in this case, going through the body, all right, so then just like what we have for linear motion or translational motion, when we say if you have a body that's moving, now if you apply external forces, then there's a response to the external forces, okay? So the mass is the measure of the resistance to the oscillation or the external forces. So then in this case, similarly, we'll define a quantity called mass moment or inertia, but this is referring to when you have a body rotating about an axis. Okay, so then T is the torque by the external force. That should be equal to the moment of inertia times the angular oscillation alpha. Okay, so this T equals to I times alpha is similar to F equal to M times A. Okay. All right. So then mass moment of inertia is a property that measures the resistance of the body to the angular oscillation. Okay. Now, to calculate the mass moment of inertia, you will use this equation here. I equals to integration of the of r squared times dm. Okay, differential element of the m here. Okay, and then you are doing r squared to it. So basically, if you have a irregular shape object, or if the density is not uniformly distributed, then you'll take the differential element of the mass, that small part, and then the r is measured from that particular part to the rotational axis. Okay, the perpendicular distance of that. Okay, so r squared. All right. I is also called moment arm. Okay. All right. And this moment, mass moment of inertia should have a SI unit of kilogram times meter square. Kilogram comes from the mass, and meter square comes from the R. It's the distance quantity. Okay. Or if you use the pound square feet system, pound feet second system, then it's in slag feet square. Okay. So in that system, the mass is measured in slag, and then the distance is measured in feet. Okay, so typically you'll use the differential element, and sometimes or more very often you'll use these two thin slide, like thin disc and thin plate. Okay, typically very often an object can be divided into small slices of discs or plates. Then you can integrate through the whole body of it. Okay, if you are using these two shapes for the differential elements shapes, then depending on which axis the object is rotating at, okay, so if you have a disk rotating with the z-axis, then the moment of inertia is this IZZ should be just equal to 1/2 mr square, okay, and then if this guy is rotating with this z prime, okay, so then it's different, it's 3/2 of mr square. Okay, so you can see if you are rotating with different axes, although they are parallel to each other, you still get different curvature at the end. Okay, and then if you are rotating your disk is rotating with respect to the x-axis, then this is equal to 1/4 of mr squared. M will be the total mass, and then R will be the radius of the disk. Okay. The same for the disk is rotating with this y-axis. Okay, so it's also 1/4 of mr squared. Okay, so if you have a thin plate on the right hand side here, then if it's rotating about the x-axis, it's 1/12. Okay, and then the same for, and then this is in, you take the length of this, the y length here, okay, of the plate. For the plate to be rotating about the y-axis is also 1/12 by m times a squared. Okay, so a squared over here. And then about z-axis is 12 of m a squared plus b squared. Okay, the sum of this and the other two. Okay. All right. So let's take a look on the concept quiz here. Let me create the breakout rooms for you guys, so you guys can have discussion about this one. Okay, and then send me your responses in the chat again. This time it could be to everyone because it's not quiz here. It's not taken as extra credit. Okay, so create forums here, automatically assign participants here, create rooms, and then open all the rooms so you guys can join. I'll be closing this in about 3 to 5 minutes. Okay? so you guys are all back, and let's see. So all of you guys said the first one should be C. Okay. So yeah, and that's right. So for the first one here, you're looking for the moment of inertia for the rod of mass M and length L rotate about a transverse axis located at its end. Okay. So then you'll be having a rod like this. Okay. And this is the axis rotation here. You'll take a small differential element of mass somewhere there. The distance from, so you'll take this as O axis, so then goes in that direction. So then for this small element, you'll be doing like R squared dm, okay, which R is the x, okay, so x squared dm, and you'll be integrating from from 0 to L, okay. Now dm will be just equal to the mass divided by the whole length, that gives you linear density times dx, okay. So then you'll be doing like I equals to that, I equals to this, from 0 to L, x squared times ml dx. Okay, m over L is the constant. So then this will give you, this is x squared, will give you 1 over 3x to the q, the m and L, the constants goes in front from 0 to L. Okay, so then it's going to be just m over L 1/3 L to the q. Okay, so L to the q becomes L to the 2. So then 1/3 of ml squared. Okay, so that's that one on C. Okay, so this is how you would do it. Okay, the second one, most of you guys says B, but a couple of you guys says A, but the correct answer is B. Okay, so let's take a look here. If you have a ring, all right, now X and Y, you are looking for an axis going through the center of the ring, so let me just draw it in this way. Okay, so this is perpendicular to the page here, the paper here, going out of the paper. Okay, so you can take a small differential element from the ring. Okay, dm. So dm will be the m divided by the circumference of the ring. Okay, 2 pi times r times the small dl, okay, from small length of it. Okay, then you'll be doing integration. In this time, the distance to the axis rotation will be r then. Okay, so integration of r squared dm, m divided by 2 pi r dl. Okay, you'll be integrating through the whole circle here. So that means it's going to be just, because all these are constants. Okay, so they can go out of the integration. It's then m divided by, or m times r squared divided by 2 pi r. Okay, and the integration of the whole ring, that gives you 2 pi r, the circumference of it, so that cancels out. Okay, so at the end, r is going to be just equal to mr squared for the ring. Okay, so then it should be B here, right? For if you got A, then it's actually the moment of inertia for a circular disk. Okay, it's not a ring, because for the disk, then you have mass distribution through the whole disk. And on the ring, it would be just on the ring. In the middle, there's nothing. Okay, so it's mr squared. All right. Okay, so anytime if you have questions, you can just unmute yourself and speak up, or text me in the chat. Okay. All right, so let's move on here. Sometimes you have the body, like rigid body, as different shapes. Okay, so then usually you'll take different differential elements. For example, you can take a shell element. Okay, if you have a cylinder, then you can take a shell element, take the thickness of this shell as d, in this case dy, okay, or dr, if you take R, then you take a circular shape at the bottom here, and then you have a shell here, so then it'll be the same as X and Y is the same as R, okay, so either way. So then you'll be looking at the volume of this shell, okay? Then you can take dV as that guy, all right? You can take the density, mass density of it, and times rho times dV will give you dm, okay? So, and then you'll be doing R squared dm again, integration of that, okay? So from, say, from 0 all the way out, okay? So that's the cell element you can take. And then sometimes you can take a disk element. You can take a small disk, all right? So then the thickness of the disk will be dz. If you take this configuration over here, then it's dz. Then you can again figure out the differential volume of this disk. Okay, dv equals to pi r square. R again will be the same as the y. Okay, so then dz. Okay, and then integrate through, if you are starting from the bottom here up to here, so then it will be from 0 to z, okay, any certain number z, okay. So shell elements are disk elements, okay, or any like the plate element, as we mentioned earlier, okay. All right. Now, also a lot of times the moment of initial about a certain axis is known, all right. And then if you are looking for the new moment of initial for the body about another axis that is parallel to that no moment of initial axis, original axis, okay? Then you can do parallel axis theorem, okay, which says the new moment of initial should be equal to the known moment of initial plus the mass of the body times d squared, okay, where d is the perpendicular distance between the parallel axis, okay? So if there's this axis, all right, and going through the center of gravity of the body, okay, and then if you have any axis, say somewhere here, it goes through, say, point A here, okay, then you can do that, okay, you can do the new moment of initial at point A through the about the axis through point A is equal to this original moment of initial through this G plus md squared. Okay, this is the parallel axis theorem. Okay. Also, sometimes you want to know like the kind of, so the radius of gyration, actually you can put this in this way, like the average distance of the mass distribution with respect to the axis rotation, okay? So you can put that in the way. So, but basically, this is define a new radius called k here, mk square, okay? So everything can be written as mk square, right? But in this case, so then you'll rearrange the terms. So you divide both sides by m, and then you solve for your k. So then k is equal to square root of I over m, okay? So to calculate radius or gyration k, you'll be calculating I first, and then divide by the mass, overall mass, and then take the square root of it, okay? So the radius of gyration has the same unit of length, okay? And then it measures the distribution of the body's mass about the axis, okay, at which the moment of inertia is being defined. All right. Sometimes you have a body that consists actually like a system consists of different many pieces of bodies. Okay, so you could have a system having like say a square plus say a cylinder, okay, or a sphere plus a cylinder, etc., or like a disc plus say a rod, etc. So then to calculate the moment of inertia about a particular axis, then you'll be calculating each part of the body or each of the shapes, and then you'll be just adding them up, okay, about the same axis, okay. So it has to be the moment of inertia about the same axis, okay. It couldn't be like one part of the body is rotating about one axis, and you calculate the moment of inertia plus another part of the body rotates about another moment of inertia. Okay, that doesn't work. Okay, it has to be the same axis of rotation. Okay. All right. Now let's take a look on the attention quiz here. Let me reopen the breakout room so you guys can have discussion about it. And then, all right, it's already open there. Okay, so rejoin the breakout rooms, and then you can submit your answers later after you exit. Okay, I'll be closing this again in 3 to 5 minutes. All right, so let's take a look here. On the first one, it says the mass moment of inertia of any body about its center of mass is always, okay? So this one, you can use the parallel axis theorem, which says the moment of inertia is going to be equal to moment of inertia to the center of body plus md squared, okay, where d will be the distance from the new axis rotation to the moment of inertia, that is the exit through the center of the mass of the body, okay? So you can see this term is always going to greater or equal to 0, okay? So then this guy, or would say it would put the I to be always greater or equal to the moment of inertia going through the center of body, okay? So this will be the minimum, okay, for any of the moment inertia. So moment of inertia through the center of body should be minimum in this case, okay? So then you would have B as your answer here, all right? The second one here says, if the mass of body A and B are equal, but Ka equals to 2Kb, then what about the IA and IB, okay? So we should know that for K, it's defined as square root of I over M, okay? Radius of gyration. So then if the masses are the same, okay, MA equals to MB, so then we just use M for both of them, okay? Now KA is equal to 2KB then, okay? So you can do ratio, you can do KA over KB, so KA over KB will be equal to 2 then, okay? KA over KB then it's going to be also equal to square root of IA over M divided by square root of IB over M, okay? The M are the same, okay, so they cancel out. So the square root of IA over IB, okay? So then in terms of IA and IB, okay, so you can do the ratio. So this is equal to 2 then, or this is equal to 2. So you can square and square the other side, okay? So IA over IB then should be equal to 4, or IA should be equal to 4 times of IB, okay? So this one then will be C. Okay, so C has that IA equals to 4IB then, all right? Okay, so I think everyone got first one right, got one right. Only like say one of the responses not right on 2, okay? But on 2 it should be C, okay? All right, so now we'll take a look on a couple examples here. Okay, so the first example here, so for the volume shown here, the mass density, okay, so when you see a rho, that refers to mass density, okay? It's 5 slugs per feet cube, okay? So that means we are using pound feet second unit system in this problem, okay? It says find moment of inertia of this body about the y-axis, okay? So this is the y-axis. Now this shape actually has symmetric, okay, around the y-axis. So then you can use a disk element, okay, about the axis of y here. All right. So if you do that, the disk element, then you are doing d I in the y direction, okay. Take a small increment in y, all right, and then take a disk here. So you're going to pick a disk here, all right, and then show me the thickness of the disk is dy, differential element, all right? So in here, then the volume of this disk will be pi r squared, where r is equal to x, okay? So so pi x squared, and then times dy will be the thickness, that's the dv, all right? dv times rho will be the dm, okay? So dm is equal to that guy. So then for this small part of it, the moment of initial, this disk element is equal to 1/2 mx squared, okay? Because for disk is 1/2 mr squared on this guy here, all right? So then for the small differential element of the disk element is that guy. So, and then you're going to be integrating. So you will take a disk from y equal to 0 all the way up to y equal to 1. Okay. So integration is to go from 0 to 1 and then take that expression over there. Now in here, the x and y's are the actually I think x is equal to so x is equal to y squared here. Okay, so x equal to y squared here. So then when you do the integration over here, so x to the 4th, that should be equal to x, y to the 8th. Okay, so you want to express this in terms of y because you are integrating with respect to dy. Okay, so rho pi, they are constants, and then 2 is also constant, so they go in front of integration. So then it's y to the 8th dy. All right. So it becomes this guy because y to the 8th would be integration of it. It would be give you 1/9 y to the 9 power. Okay, and then becomes this guy here. Okay. All right. So yeah, let me see. And then the phi should be coming from rho, I think. Yeah, rho is equal to 5. Okay, so phi, so it's pi rho basically divided by 18 because your upper limit is 1. 1 to the 9th power is still 1. Okay, so that equals to that guy. So for the moment of inertia about the y-axis, okay, so 0.873 here. Okay. Questions? Anyone has questions on this one here? All right. If not, then we'll take a look on a second example here. So this one says if you have a pendulum consisting of a rod and then a plate, a circular plate. Okay, so this is a cylinder rod, this is a circular plate. This guy is 2 kilograms, this guy is 4 kilograms. The pendulum's radius, so find the pendulum's radius of gyration about and exit perpendicular to the screen and then passing through point O. Okay, so it's about this guy. All right, so you're looking for radius of gyration. That means first you want to find the moment of inertia with respect to the axis rotation. Okay, so there's a axis rotation going through O here. Okay, so let's take a look here. Now you have a system that consists of 2 parts here, a rod and then the disc. Okay, so you can calculate the moment of inertia for a rod with respect to an axis going through O, and then calculate the moment of inertia for this disk about the axis 2. Okay, then you can add them up. All right, I think that's the plane here. So for this guy, for the rod, okay, so then the center of the gravity for the rod should be at the middle point. Okay, so then this guy, so so then if you are looking for the moment of inertia for the rod with respect to this O, okay, you'll be doing the moment of inertia through the center of gravity plus md squared. Okay, so for the rod, and then you'll be doing also this for the circular plate as well. So for the rod here, it's 1/2 or 1/12. Okay, so if you are looking for exit going through the center of the rod, okay, which is the midpoint of the rod, okay, that's going to be 1/12. Okay, you can calculate this by, let me see, it doesn't give you directly, but you can calculate this. Okay, so by doing because this is the rod here, and I know many of you guys have learned this already in physics, but let me just tell you guys how to do this again. It's kind of review of for those who haven't taken physics, then you know what to do here, okay? So we will take a exit going through here. Now, assuming the exit is going perpendicular to the paper here, okay? So then we'll take that as the origin, all right? Going to be like we can say this to be positive, the other side should be negative. All right, so you're going to pick any differential element here, length of ds, all right? So then you'll be doing r squared dm, going to be the I. You're integrating, so this is from -1/2 L to the positive L, 1/2 L, okay? So this is negative side to the positive side. So R is this guy, so R is always going to be X, okay? So then it's X squared dm is equal to, dm should be equal to the mass of the rod divided by the length times dx, okay? The linear density, mass density times the length, okay? So then it's dx times m over L. And then integrating from -1/2 to +1/2, okay? So again, this is x squared, so integration will give you 1/3 x to the q. The constant term will go in front of integration result, okay? Then you're going to integrate from -1/2 L to positive, okay? So then this is all the small m, either way, capital M or small m, depends on what's given. So 1/3 L to the L half to the q minus, okay, 1/3 minus, there's a minus sign here, to the q, okay? And then all this together, all right? So this then will give you L to the q over 8, 1/3, minus become positive, okay? Again, L to the q over 8, okay? And then multiply by m divided by L, okay? Now this is 24, okay? 1/24 plus 1/24 gives you 1/12, okay? So ml times 1/12 L to the q, okay? And that cancels out with square remaining, okay? So it's 1/12 ml squared, okay? So then this is where this is coming from, this term here, 1/12, okay, on the PowerPoint, that is coming from here, 1/12, 1/12, m is 2, the length of rod is 2, okay? Plus 2 times md squared, okay? So 2 is the mass of rod, and then d is the distance from the new axis rotation to the axis rotation through the center of the gravity, okay? Which on the rod should be through this guy, okay? So then that's 2 times 1 squared, okay? So this is moment of inertia for the rod with respect to the new axis rotation O, okay? All right. Or you can use what we got from the earlier quiz, concept quiz, where the rod now is rotating with the end, x going through its end, okay? So then that's going to be 1/3, 1/3 of m times L squared, okay? Which will also give you this result, okay? Either way. For the plate, for the so you can take again the center for the yes, sir.
Yeah, so how did you know that it was L/2 again? Is that just length over the distance of the pole, that's it? Is it always going to be like that?
Did you say the 1/L/2, which one?
L/2, how'd you know that that was your integral from negative L/2 to positive L/2?
I see. So because you are integrating, your x rotation is at the center of the rod, okay, going through center of rod. So you are going to pick that as your origin, okay? So then you are from -1/2 to +1/2.
Okay.
Okay. So if your x rotation is on this end, then you're taking that as your origin. So then you'll be integrating from 0 to L. Okay.
Oh, got you. Okay. Yep.
Okay.
Thanks.
Great. All right. All right. Now on the plate here, because it's a circular disc plate, okay, So then you'll be doing similarly the disk for the disk, okay? You can also, if you want, you can also do integration by yourself, okay? But for the disk, it's m1/2 m r square, okay? So 1/2 m is the mass of the disk, and then the r square. Now that's the moment of initial through the center of the disk, okay? The new x rotation is over here, so then you want to plus, according to parallel axis theorem, you want to plus md square, okay? So m is the new m, the 4, d is the new distance, the 2, plus the r here, okay? So that's the distance between the two axes of rotation, okay? So then that will give you 25.5, all right? Then you're going to add the 2 up, okay, to be the total moment of initial about this new x rotation through O, okay? After that, you're going to calculate your radius of gyration, k equals to square root of moment of initial about this O axis, the x going through O, divided by the O overall m, okay? So overall m should be 4 plus 2, which is 6, right? So that means for the new x rotation, the direction of radius of gyration is this guy, 2.17. Okay, so that tells you it's about, or you can take this as the average mass distribution through about this new axis. So it's going to be somewhere here. Okay. All right, so that's the second example here. Any questions you guys might have? If not, then we're going to be looking at the group problem solving here. So another example here. So this one is very similar to the previous example, but this one now you have a rod, you have a rectangular plate. Okay, so basically you'll be following through the same procedure. You'll now it's asking you the radius of gyration through this center of mass for this system. Okay, so first you want to figure out what's the center of mass where this is. Okay, given if this is y, okay, you have starting from this guy, you can set that as your origin. So this is 0 in y, and then this could be the positive y direction. Okay, we can take that as the coordinate system. Now to find the center of mass, okay, let's find the center of mass first. So let's define where this G point is in Y. Okay, so we can do, there are two parts of it. So to find the center of mass, you are going to do if there are two, so M1, Y1 plus M2, Y2 divided by M1 plus M2, okay? So this will be the center of mass of the Y. Okay, y sub g. Okay. Yeah, and then you're going to just plug in the numbers. The first one I think is 3. Okay. And then y1, y2 will be the center of mass for each parts of the particle. Okay, so for the first one, the rod, it's going to be just 1. Okay, because the rod its length is 2. Okay, so then the center of mass should be at 1. Plus for the rectangular plate, so the mass is 5, and then it's 2 for the plate. It's located like 2 for the rod, and then you'll take half of the weight here. Okay, so 2 plus half of 0.5, so then it would be 2.25. Okay, divide by 3 plus 5, that would be your center of mass. Okay, 1.781 meters. Measure from the point O, okay? So now you are going to calculate the moment of inertia for each of the two parts with respect to this new exit going through G point, okay? So you're going to do I of the, say, point rotating about G point for the rod. You can do it that way. Okay? You can also use the parallel axis theorem. So it's going to be for the rod, if you know through the center of the mass is 1/12 m of the rod times the length of the rod, okay, and then plus m of the rod times this new distance d. Now you can see that would be yg, okay, the center of mass of the whole system minus the center mass of the rod, okay, square. All right, so then you can plug in the numbers. 1 over 12 times 3 times L would be 2 square plus, again, 3, and then times this guy, 1.781 minus 3 squared. Okay, so because you are going to square it, so it doesn't matter. Okay, you can put 3 in front, or actually 1, I'm sorry, not 3. Okay. All right. So then this will give you 2.83 kilogram times meter square. Okay. Now for the I of the with respect to G on the plate, okay, you can do the same thing. For the plate, you can take, so for the plate, a plate like this, okay, you can assuming the X rotation is going through its center, okay, then this is like the, say the X, this is the Y, okay, then you are looking for the I with respect to Z, okay, so I of Z, okay. You can look this up in the slides before, like the very beginning of the class, okay? So let's go back a few slides. No, not this one. Okay, on this one here, okay? So I with respect to ZZ, okay, the Z axis, the plate, this is going to be 1 over 12, okay? The mass of the plate times A squared times B squared, okay? You can take that one and then apply to what we have here, okay? Or you can do, fundamentally, you can take a slice, a very thin slice from the plate. You can do integration through the, if you take the slice of the horizontal slice, you can integrate through the vertical, okay, the Y, okay? And then let me see, over here, okay? So you can take that, and then so now this will be just I of this ZZ, okay, plus I or M again plate, okay. So then from the new Y of G minus the Y of the plate, okay, would be Y2 squared, okay. So you can plug in the numbers, okay. I'm going to just skip the plug in the numbers, so you take this one over there and then plug in the numbers, and then this is going to be, I have it somewhere. It's going to be, yeah, 1.6206 kg meter square. Okay. Then you are going to add these two up for the total I with respect to G plus I of G to of the plate. Okay. You add the two up. Okay. It's going to be 4.45 kg meter square. Then the K will be square root of this IG divided by the total M, okay? Remember, it should be total M. And then plug in the numbers, you'll get 0.746 meters on this one, okay? So I'll post the full solutions later, okay? But I'm skipping the plug-in numbers over here, all right? Questions you guys might have?
Can I see what your K value was again?
0.746.
Thank you.
All right. All right. If not, then I will see you guys on Wednesday. All right. See you. Bye.
See ya.
Dr. Park or Dr. Ho.
Yes.
Messed up. Sorry.